So our next talk here in this session is from Konstantin Berlin. He's a director of data science at Sophos, and he's going to be talking to us about different issues with malware labeling. So please welcome Konstantin. Thank you.
Thank you. Yeah, I guess I moved on from data science to AI at this point. I guess a little bit about myself. I've been at Sophos for 5 years, if you count, I guess, 2 years at Invincia. I'm a director in the data, what we call Sophos AI group right now. And what I do every day is basically, I don't do as much ML research, though I still do that. What I mostly spend time doing is thinking about how we take our research and how do we put it in production. Because in the end of the day, right, everything we research, we have to put in production. And the big thing about putting things in production and enabling our team to come up with these models is that it's a highly complex process. And I think of my main job as basically a force multiplier for my team, which is we have so much human resources. How do I make everyone just go much, much faster? Let them do as much research as fast as they can, right? Without being blocked by infrastructure woes. The problem is, in my job, is that it's a super complicated problem. And it's because we have a lot of data. And not only do we have a lot of data, we have a lot of data that's coming from different parts, from different feeds. You have intelligence feeds, like let's say VirusTotal. You have internal feeds, whatever they may be. Maybe it's telemetry, maybe it's something. Yeah, well, so maybe it's your analysts. You have your product telemetry, which is huge. You're just pulling huge amount of information about what's going on endpoints. And if you're Sophos size, then you have hundreds of millions of endpoints that are streaming you this telemetry. And the other problem is that it's not your typical problem, and it's because the information that you have, not only is it spread among multiple feeds, it also happens to spread over months or years, right? So for example, you might have seen a file in VirusTotal a year ago, and then it shows up in your customer telemetry a year later. And you still need to know that, oh yeah, I've seen that one, and this is what the industry thought about that file a year ago. And now maybe I can link that information together and somehow form what we call a label. And so the complexities are, like I said, like one is you have multiple feeds, the other one is data size. It's huge. If you don't do something right, your cloud infrastructure costs are just going to go through the roof, right? It becomes unaffordable. Labeling. So typically, when most machine learning problems are, you're trying to figure out if something is a dog or not, the label doesn't change, right? You have your data set, you store your label with your features. It's a dog, it's a dog, it's a dog. Not so in ML, right? One day it's malicious, the other day it's benign, then maybe it flips again to malicious, flips to benign. There's other information about the file that's constantly coming in, and you constantly have to aggregate this data to form some sort of the best possible decision that you can make about the file, and you're possibly updating labels every day, basically. You have a huge data set, and labels are constantly changing. And then you have this other problem, which is you need to validate your data sets. And you need to validate your sets against all incoming information that's constantly coming in. You need to see how you're doing per day. And then you need to compare yourself, let's say, to how you're doing. You need to understand how you're doing. And for that, a lot of times what we do in machine learning, we need to roll back time. We need to understand what the state was during the detection and combine it with your current best label. So you cannot just keep the latest information. You also have to have almost all information so you can perform this you have this magical ability to roll back things to the state that were at detection time. And that's super complicated and super expensive. And then, if that wasn't hard enough, then they layer this GDPR requirement on you, which is basically you can't really move data really easily, right, between regions. So it's very, very hard to aggregate data. And if you're an international company like us and you have customers all over the world. So I'm going to talk about some of the infrastructure that we build internally to Sophos AI. It's within our group, and we built it ourselves, and we special purposed it for what we do versus, let's say, what a typical organization does in their large cloud infrastructures. And because we're not a huge team, we kept it super, super simple, using as few components as we could possibly manage, make sure that it scales, and make sure basically that it uses existing technology that we don't have to upkeep. So I'm going to talk about everything we do is basically built out of pretty much these four things. We have the SQS, which is this basically distributed queue. So what you have is for example, multiple sources that can stick data into this queue. And then on the other end that's coming out, you can have a cluster sort of pulling from that queue at the same time, right? So that's a good way to manage your workflows. There are a lot of mechanisms built into this queue where if any of your component fails, you sort of have 14 days to get your system back up and running, right? So if things go down, your guy's on vacation for a week, he comes back, he fixes it, the whole thing automatically sort of fixes itself, right? Because we don't have this like support team that you can call up in the middle of the night and say things are going down. You have like 15 minutes before the whole thing blows up, right? Then obviously you have your S3, which is basically the cheapest way you can actually store data in the cloud, right? And actually S3, it has this ability not only to store data, but it can automatically move it from hot storage to cold storage, which is even cheaper, right? So if you don't touch your data for a while, it gets into a cheaper layer, which is very important. So but now you have to think about when you can touch that data and how and like what kind of data you should be touching. And then you have your spot auto-scaling clusters, right? So everyone is familiar with EC2, but that's on demand. So you want to go cheaper. You want to go to spot cluster, which is much cheaper, but they reserve the right to shut down your node within 2 minutes. But that doesn't matter because we have a cluster. So every time a node goes down, we spin up another one, right? And the technology for auto-scaling, bringing back new nodes, it's already built into AWS, right? So it's not something we have to manage. And then finally, we need to index that data, and I use the term here loosely index. We need to be able to access it at a reasonable time frame, slice it and dice it. And the most important thing to know is that there are basically two ways you store data in the database. One is row-oriented, and the other one is column-oriented. And what you want column-oriented. And the reason you want column-oriented is because what you want to do is you want to store as much data as you can, but typically you only need 1 or 2 fields from that data to actually form a decision or, let's say, create a label. And because you're able to store it in a column, it's all the same data type, so you can aggressively compress it. So whenever you have a database and you have a huge database, your number one cost center is actually storage. And because now you're compressing it aggressively, your storage costs decrease significantly, probably by an order of magnitude. And now you're not talking about storing things for a month, you're talking about storing things for years, right? So you're able to increase the amount of data that you can look at by an order of magnitude. And like I said before, it's very important because sometimes the data comes a year later, right? You've seen it a year ago, and now you're seeing it. And it's a little bit finicky, but it's a managed solution, which is the important part here. And it's super cheap. The other part here, maybe I should speed up, but basically it's the basic paradigm is data lake first. The number one mistake we have seen internally, not internally, but internally to our organization and everywhere else, is that people, they have a stream of data and then they stream it into a database. But the problem is once you put it in a database, you cannot get the data out, right? You can get pieces of it out, but if another team says like, well, wait a minute, I also want this data, and I want to store it in my database. You don't want them to go to your database and start pinging it at an aggressive level, because you're going to be paying huge costs. You're going to take down your database, basically. So what you do is you bring it into the most scalable sort of solution known to man, which is S3, right? And then everyone feeds from there, and then you feed from there. So you never put data just in your database. It's always in S3, and that way you can change your database technologies very easily, right? Just throw out your database and you reindex from S3. You can easily share this data among teams, and each team has their own cost center, so they just go into S3 and they spin up their own database. You attach a queue to that. Basically, every time there is a creation event, you get an event message here. Then you have an auto-scaling cluster that reads from this thing, gets the object, processes it, batches it together, and pushes it further down the stream. And the other cost-saving strategy is batching, and that's because you're typically paying per transaction. So if you can take a bunch of transactions and compress it to one transaction, you just reduce your costs by an order of magnitude. And everything becomes quicker and more efficient. You can even perform batch operations on the individual endpoint. And it's much cheaper to actually insert data in batches into databases. And it's all managed. It's all fully managed, basically. The components stay up. And you let the engineers, basically, and your data scientists work on more interesting problems than keeping up the infrastructure. So the typical workflow sort of works like this. We minimize costs, minimize maintenance, and then the most important part is the scaling. One mistake you can make is you have a data flow, and that's what you think is going to be. And then you think, okay, maybe it will double at some point, right, as more and more customers go in. But the big problem is sometimes you make a huge mistake, and you need to go back and you need to repopulate months and months of data. And if you're only able to go twice as fast as your normal flow, to populate a year's worth of data will take you 6 months, right? Pretty much. Maybe even actually slower, because you also have to keep up with the current flow. So what you want is this system to be infinitely scalable, basically. Populate 6 months in days, maybe a day. Just make the trade-off. I want to pay a lot of money, I'm going to spin up a lot of things, but I'm going to finish the job within a few days and correct the huge mistake that I made earlier by not including this or this data, for example, in the data flow. And that's the thing. And then you have to deal with the regional sort of issues in GDPR. So what you have is you have a data, you process it locally, you do whatever you need to do, you store it in a bucket, and then you replicate it across regions. Because when you replicate across regions, instead of copying directly into across regions, the AWS pays for the CPU cost of transferring data. So it's much cheaper and much faster to replicate a bucket than it is to directly place into buckets outside your region. And so you take it off, you take it to your home base, you store your blobs, you push your metadata into your database, and that's basically the system that drives everything. And it sort of looks like this, right? You have petabytes of artifacts. So that's your files, everything that's your original data. Then you have your feature vectors. Every time you have a file incoming, you extract your feature vectors. The reason is, once you put it here, you're going to push everything into intelligent tiering. So you want to stop touching files when you do research or when you release new models. Right? So you store the feature vectors, and whenever you train a new model, you never touch this bucket. You only touch this bucket to get the feature vectors. And this bucket is much smaller, so the cost to have this bucket is much smaller than to have that bucket be in warm storage. Then obviously, you never ever put everything in a database and not have a backup in S3. So you have your sort of metadata in here, so you can change databases. And finally, you have your indexed, I quote, indexed data in your database, which happens to be Redshift, because it's columnar. Once it's columnar, you significantly decrease storage costs. And then, that's, I guess, step one. Step two is, how do you actually use Redshift? And it gets a bit complicated, but what we do is we have basically, every intelligent feed that comes in gets put in its own table. And then what Redshift is really, really good at is joining information together. And in the end of the day, right, the thing that makes this problem more difficult than you would typically see is that you're joining information across feeds. That's a very, very expensive thing to do, and it's super expensive for a database to do. And Redshift, if you lay out the data, is among one of the fastest, most scalable solutions for that, because it's a distributed database where the data is sorted by the key. So it basically becomes this merge operation, which is super fast, assuming you can maintain sort order in your thing. And so we make sure we lay out the tables correctly. We make sure we get the right distribution key, because it's a distributed cluster. We make sure the sort order is correct. We maintain that sort order aggressively in the background by constantly vacuuming the table. And then we go in, and then we clean, we do this weekly cleaning of redundant data in the database. Because sometimes you double stream something. Sometimes you have a lot of older data that you can no longer retain, so you have to delete it. But it's simple enough. And then we do daily aggregation. So we aggregate, and we compute all the fields that we actually care about. And actually, we compute more than all the fields we care about, because this table can be very wide. Because when you're pulling data from this table, you're not going to load the whole row every time you make a query. You're only going to load the data that you care about. And so even if your table is super wide, the queries remain fast as long as they don't access all the columns, right? And for example, if we aggregate this data nightly and we have a column called is it malware, right? Then to actually pull a data set, all we have to do is look at that column, which is an integer column, which we can pull literally billions of rows very quickly. And what are some use cases for this thing? Well, so originally when we started, we had one model, which was the PE model. We are up to we're getting close to 24 models that we have to train all the time. So we have this database that contains all the data that we know about, and we have to constantly slice and dice it in different ways to get data sets for each individual model, which use different sums. So we store things like, is it malware? What file type is it? How do you know what file type something is? Well, it's a complicated question, right? So we have things like, we have a stream from VirusTotal, which tells you what the file type is, but that's not enough necessarily. We have another stream internally coming where we basically process every file that comes in, and we extract metadata for it, including file type. And then we compare the VirusTotal file type, the reversing file type, our own internal file type. And then you can make a complicated SQL query that sort of renders the final decision. Like, this goes for this model, this goes into this model, and this goes into this model, right? And you can pivot that decision. You can change that decision, and within an hour or so, everything is completely updated and refreshed. So we are able to constantly update our decisions. So we use it for labeling. So we define the final label, and we use that label by joining every source that we know about, and then using somewhat complicated logic to figure out what the final label should be. Right? So it's not just a decision based on VirusTotal. It's not just a decision based on our internal labeling. It's a combined decision. It's a decision based on what we see in telemetry. It's a decision that's, combines reversing labs, VirusTotal, everything you know, analyst, feedback, that also streaming back, right? And it's just a simple SQL query to actually come up with that label in the end of the day. And I can change it tomorrow if I see I made a mistake, right? And then, obviously, we use it to get training metadata. So you're able to, from Redshift, you're able to export data out at scale very quickly. Because what it does, it simply takes the rows and it just dumps it into S3 in a distributed way. So you can get data out very quickly, hundreds of millions of rows within a few minutes. And then, to To define a training set is just a simple SQL query into this database. That's how we define the entire training data set. Gets updated every day, and every day it's just a pull request. It's just a SQL query to get the database and unload it up into S3. And then, because we have all the information right there at our fingertips, we're also able to sort of realize where pieces of data are missing. We're able to grind for billions of rows very quickly and try to fetch the missing data or fix any problems, and so on. We also use it to drive the dashboard, for example. So we have a dashboard where we monitor performance, and it's very easy to do because we know we have all the data in a single place. So we can compute the labels, but we can also compute first seen behavior for our models, for competitors, God knows, for everything that we know about. Right? And it's there, and so for example, you can see the data filters, right? We can pick the data source, right? We can see what file type. We can pick the label that we want, right? You can try different labels. And we don't pre-store this data. This is actually a live query that goes, a SQL aggregation query that goes in, and within a few seconds is actually able to render everything, full detail over months and months of data, right? And it's super powerful, and I think it was a game changer about, like, in terms of improving our efficiency. Yeah, and that's how sort of our internal workflow works. It's a very simple system made up of, as you saw, 4 components that run together, and they're completely managed, and it's a hands-off system.
Just a quick question on the dashboard. I've built similar systems and I'm trying to do some dashboard stuff myself. And for calculated metrics like efficacies and stuff, what do you actually build that on?
Redshift.
And that does all your visualization.
This? Oh, this? I'm not a visualization person. It's built on top of a D3 JS. Is that a thing? D3? D3, yeah. Yeah.
So a question around using Redshift and S3 and the interactions. Did you guys consider using Athena and writing Parquet to JSON? Or
Yeah,
did you
much
try that?
complicated, much more complicated, not as robust. The trick is actually we have to maintain sort order, so we're constantly accessing files. We're not accessing files, we're accessing blocks of disk space and constantly sorting them to make the aggregations more effective. So you will pay insane amount of cost if you try to do the same thing for S3 Parquet files.
Oh, thank you. That's very interesting.
For your longer running tasks, you said you build nightly. If you have a distributed team, are you able to identify times when you can basically bring the system down for those longer running tasks easily, or is that a complication for your team?
The system does not go down for these aggregations.
Okay.
It's just a join. It's a multi-table join operation in SQL, and we just basically create a new table and then replace the old table with a new table.
Hey, a ton of great information here. Had a bit of a question. So, for those of us who don't want to give all of our money to AWS for GPU, and I swear I don't work for NVIDIA, so I'm not trying to tell you to buy those. But for people who have on-prem stuff, especially for GPU, do you have any insight or thoughts about how sort of the stuff that you're talking about here would interact with that, or have you given any thought to how to most efficiently sort of combine your AWS resources with your on-prem resources?
That's a good question. So we don't like giving money away either. We don't have our own on-prem because, again, we're minimizing maintenance. We used to have our own cluster. It was hard to maintain. But the the workflow is the same. We pull the data out, right? And it's not necessarily a huge cost to pull the metadata out, right? Because it's not large. You're talking about, less than a terabyte usually for very large databases. Then you have to figure out how you get your features. So we store the features in S3, and then we pull that down. And obviously, because our EC2 node is co-located with a S3 bucket, it's free. But since you're running on-prem, I don't know what you do. But if you can store it on-prem, that's up to you. Yeah. So I mean, there is a reason why Amazon makes it free probably to pull from S3, and that's because they want you to use EC2 resources. And whenever you do that calculation, it's always just a little bit cheaper to not have your own thing. And it's not an accident.
Yeah, thanks. That was actually a very interesting talk. Thanks. So you mentioned 2 quick questions, by the way, also, right away. You mentioned petabytes of data in your cloud. So how do you get this data to the cloud? And here I'm curious whether you choose like a direct connect, Snowball, like a combination of those, maybe a different way.
How do we get the data in?
Yes.
I mean, so it comes from the intelligence feeds, for example, you pay for, right? But you have an EC2 node running that pulls the data.
Oh, so you generate it like right there, right?
So
You're not transferring lots of data from like a client, right?
well,
just
you're
generate it
also
in the cloud.
transferring from. I mean, you're collecting telemetry. There's limitations of what you can take from the client.
So how do
due
you
to privacy restrictions?
Right. How do you transfer, let's say, 100 terabytes of data to the cloud? Are you using Direct Connect, or you just buy a Snowball, Edge, and send it in that like suitcase or whatever? Or you don't know that. I mean, I don't know.
The reason I'm having problems answering that question is it just depends on who you're pulling from and who pays, right? So if you're subscribing to an intelligence feed, right, they're running the servers, and you just pull from those servers, and as part of your fee, for example, that you would pay to VirusTotal, right? You have access. I can pull X amount of files, let's say, from VirusTotal, right? And they're hosting it. They're paying for that. To pull files into AWS, it's free. You just have to pay for the CPU cycles of the EC2 machine that's doing it.
Yeah, that's another good question. Yes.
Daily. That's a good question. I would assume it's in the dozens. Do I want to say dozens of terabytes? But close to that, maybe less. Yeah.
Well, yeah. Then I would probably choose Direct Connect. I don't know. Anyways, so the second question would be, it's a very quick question. Was Elasticsearch slower than Redshift?
Elasticsearch, so don't want to offend anyone here. So Elasticsearch, right? It's not a columnar database. So it's you're gonna pay. So one of the common problems with Elasticsearch is that you have to pay a lot of money to store data, and we have to store a lot of data, right? The other part is joining the data, right? We are constantly having to join different sources together, and maybe someone can explain to me, but it didn't seem like Elasticsearch is the best way to join different feeds together on a daily basis.
Thanks. Can you comment a bit on, so you got your training set after all this machinery, what kind of tool sets and software stack do your researchers use after you got your data that matches what you have here?
Okay, yeah. So what we do is we have and we're hoping at some point to release this as open source. We have our internal, tool set called Dataset, and Dataset is an abstraction on top of the metadata and the feature vectors, and it allows it's sort of this abstraction layer. It doesn't care where you store the data, whether it's locally or globally. We happen to do it locally because we're constantly randomly iterating it, and it's usually much faster to read from a local disk than to read from a cloud solution. So there are questions about how you would store in the cloud that would scale and so on. But so we have our basically abstraction, and then on top of that abstraction, we have these connectors that, for example, connect to PyTorch or connect to whatever, Keras, whatever you want. It's just like insert data set here, Dataset is this abstraction about here's how I get labels, here's how I get weights, here's how I get features for a specific batch. Dataset lets you slice the data very quickly because when you're doing, neural network training, you're constantly slicing randomly your data. So that's what it is. Like Dataset lets you pull down this stuff plus feature vectors and let it slice very quickly. And it paralyzes all the stuff for you in the background. And we have a collector that collects the stuff and puts it into a data set. That answers the question.
I just want to get some clarification. When you have the slide that has like multi-region setup, so here, is it like for different data types? Do you have like also replications for the pipeline for different data type?
So each pipeline for each data type is exactly the same,
Yes.
except the logic of how you transform it is different. So if it's metadata, then it's we strip out the PII information and then we potentially flatten it and then take it to our database. If it's blobs, then we don't do much. We just replicate it into, if we can, we replicate it into a central bucket.
Have you thought of using glue, or how it's different from glue?
We thought about using glue. It was hard to use. It was hard to use, difficult to set up. And again, the secret sauce here, this is an auto-scaling spot instance. So it's much, much cheaper than spinning up a cluster necessarily.
Okay, thank you.
And you're not constantly, so like if you contrast it with Spark workflow, you're constantly processing incoming data. So you're just maintaining this cluster, constantly getting feeds from SQS and not Kinesis, because Kinesis is more expensive and not as resilient.
Okay, I think I saw a couple other questions, but we're at 10:30 now, so anyone else who has questions for Konstantin, please feel free to hit him up during the coffee break, and we'll be back here in 15 minutes, 10:45, 10:50 to start for the keynote. So, thank you.